ਅੱਜ ਦੀ ਇਸ ਲੈਕਚਰ ਦੇ ਵਿੱਚ ਆਪਾਂ ਕੈਨੋਨੀਕਲ ਇਨਸੈਂਬਲ ਦੇ ਬਾਰੇ ਗੱਲ ਕਰਾਂਗੇ and then we will derive the partition function. So in our previous lecture we have discussed about the microcanonical ensemble, so in which the macro state they are determined by the fixed energy range, and then its thermodynamics which we have derived by finding out the value of entropy. But in actual, the concept of fixed energy and fixed energy range, it does not apply satisfactory. So now there are basically two problems that why microcanonical ensemble does not provide efficient results. So first is, in real world, total energy of the system is hardly ever measured. So it is very difficult to measure the exact value of total energy. So total energy of system is hard to measure. And the second major problem is it is very difficult to keep the value of energy under the strict physical control. So to keep the energies under the strict physical control. So like in the microcanonical ensemble, we have said that the energy values they lie particularly in between these two limits, but in actual it is very difficult to keep the energy limits by applying these fixed constraints, because the energy values, so they are quite varying in actual in real world. So a far better alternative is to measure temperature of the system, which is not only the direct observable but also controllable. So it is easy to observe the temperature and easy to control. So it can be easily measured. How we can easily measure it? So using the thermometer, so we can easily measure the temperature of any system, and we can easily control the temperature with the heat reservoir. So we are keeping our systems in a big heat reservoir, and it is very easy to judge or to measure so how much system it is losing heat to the heat reservoir, or how the system it is gaining the heat from the heat reservoir. So if the heat reservoir consists of an infinite large number of mental copies of the given system, and then it is an ensemble in which the macro state of this system it is defined through the parameters, that is n, v and t. So those systems, those infinite large number of mental copies of the system in which the ensemble, the macro states of the given system, they are defined through these three parameters, that is n, v and t, and such an ensemble is known as canonical ensemble. So in such ensemble, energy of the system it is variable, and we generally keep these values of the energy between 0 to infinity. So the energy it is variable in canonical ensemble. Now the major question arises is, what is the probability that at any time t of a system, when it is found to be in one of the states that is characterized by the energy value, and how the probability that the microstates of these canonical ensemble they are changing their energy with respect to time. So we need to establish a relation between this PR and ER. Now this dependence of the probability on this energy exchange, it can be determined by two ways. So first way, it is regarding the system in equilibrium. So if we keep the system in equilibrium with heat reservoir at a constant temperature T, and then we will study the statistics of the energy exchange between these two, and study the statistics between this heat reservoir and the systems. And the second way through which we can measure this relation between this PR and ER is the regarding a system as a member of canonical ensemble, in which the energy it is being shared by n identical systems. If we keep a large number of identical systems within a system, and then we will check how these systems they are exchanging their energy with one another. So we will establish a relation between this probability density distribution with respect to energy, and we will apply this first approach, and we will establish a equilibrium between a system and a heat reservoir, and from that system we will find out the probability density distribution function. So let us do our first way to establish a relation between this PR and ER. So that is the equilibrium between a system and a heat reservoir. Now in this case we will consider a system which is immersed in a heat reservoir. So this big, it is a heat reservoir. Let us say it is A dash heat reservoir, which is having a energy value fixed at a particular time T and temperature T. And this particular small system, let us say this system is A, and it is immersed in this large heat reservoir, and the energy at that particular point of time, that is ER, with respect to energy of heat reservoir that time, that is ER. So a system which is immersed in heat reservoir, and on attaining this mutual equilibrium, this system and the heat reservoir they will have a common temperature T. At any time now, at a particular time T, the energy would be variable with the values which is lying between this 0 to E naught, and E naught, suppose that is the composite energy of this system and the heat reservoir at now. So let us define. So at particular instant of time, this system it is characterized by energy ER. So this is the energy of system at a particular instant of time, and the reservoir which is having a energy of ER dash. And the total energy of this whole system and heat reservoir, or of whole this canonical ensemble, so that is ER plus ER dash, which is the total energy of this composite system, and that total energy it is being constant. At some cases when this system it is being exchanging the energy with the heat reservoir, so the value of this ER and ER dash, so it is being exchanged with one another, but the total energy it is always conserved, so it is constant. So let us say this is equation number 1. Now the reservoir which is much larger as compared to the system. Therefore the value of ER, it would be very small as compared to the fractional value of ER, or you can say this is very small as compared to the total composite energy E naught. So we can establish a relation. So let us, I divide this equation 1. So with respect to ER over E naught plus ER dash over E naught. So that is equal to 1, and from that you can see that ER over E naught, that is 1 minus ER dash over E naught. Since ER over E naught, that is very less as compared to this composite total energy, so therefore this 1 minus ER dash over E naught, so that will be very small as compared to 1, and let us say this is our equation number 2. Now the states of the system A having been specified, the reservoir A dash can still be in any one of a large number of these particular states, and which are comparable with this energy value ER dash. Now let the number of these states be denoted with a term, that is omega dash, which is dependent function of this ER dash, and this prime, it shows that the functional form may depend upon the physical nature of this reservoir. So the value of this microstate, so it is dependent upon the nature of or the type of heat reservoir. Now in a particular ensemble, the larger the number of these macrostates, the larger the probability of heat reservoir, assuming that particular value of energy E dash. So this we can say that is equal to the relative probability PR. So PR, it is directly proportional to dependent upon this macro states omega dash ER dash, or we can write it as PR, which is directly proportional to omega dash E naught minus ER. Now in order to satisfy our equation number 2, so that is 1 minus ER dash over E naught, so this is our equation number 2. So we carry out this Taylor expansion around, considering the value that the total energy of this system, it is very small, therefore the total energy of the composite system, that is almost equal to the energy of this heat reservoir. So using this Taylor expansion, so Taylor expansion is generally a function fx, so that is fa plus f dash a over 1 factorial x minus a plus f double dash a, the double derivative, over 2 factorial x minus a dash square, so and so. So our log of this omega dash ER dash, so this comes out to be log of omega dash E naught minus ER. So this we can write out as log of omega dash E naught plus curly log of omega dash over curly E dash, where this energy function E dash, that is equal to E naught into ER dash minus E naught. So this equation log of omega dash er dash. So this becomes log of omega dash into E naught plus curly over. So using this equation, now I am rewriting this equation, that is curly over curly E into log of omega dash. So ER dash minus E naught, so that is equal to minus of ER. So this we can write it from here. So let us see, I will write it here. So we all know that log of, if I write it curly by curly E log of omega, so that is equal to, if I multiply and divide this with k log of omega, so this k log of omega, that is the entropy. So this equation becomes curly S over curly E, and this curly S over curly E, that is equal to 1 over T. So this becomes 1 over KT, and that is equal to this beta value. So curly log of omega over curly E, so this function, this becomes this beta function, and we can rewrite our equation as log of omega dash, so that is equal to log of omega dash for this composite system minus of B into ER. Now moving this toward the left hand side, this equation becomes log of omega dash E naught minus log of omega dash ER dash, that is equal to beta into ER. Now this, the minus sign of log, this comes into the denominator over omega dash into ER dash beta into ER. So we can write it as omega dash over E naught over omega dash into ER dash, that is the exponential function of beta into ER. So this beta into ER, that is the connection between this temperature and the energy value of this system. So we can rewrite this equation as omega dash into ER dash, that is 1 over exponential of beta ER into omega dash into E naught. So this is the function or this microstate for this composite system, and E naught, that is a constant value. So we can write our relation that the energy of this heat reservoirs, it is directly proportional to a function of exponential beta into ER. So this omega dash, that is dependent upon this probability density function. So PR, that is directly proportional to omega dash ER dash, and this omega dash ER dash, that is the exponential of minus B into ER. So here I would like to tell you that, so this, when exponential, it is in the denominator, when we write it in the numerator, so this comes out to be exponential of minus B into ER. So PR, that is directly proportional to exponential of minus B into ER, and this is the connection between this relation PR and ER. Now PR, that is the maximum probability for a system at which there are the more number of microstates, so it is 1 in the state of equilibrium. So PR, So this we can write it as, so just a minute, so PR, so when I open this, so this is a constant function exponential of B into ER. Now putting the value of this PR, this comes out to be C into e raised to power minus B into ER, that is equal to 1, and C is a constant, so it comes outside the summation, so this is equal to 1, and this C, it comes out to be 1 over summation of exponential of minus BR. So this relation of PR, it comes out to be exponential of minus BR over summation of exponential of minus B into ER, where this denominator term, that is generally known as the Boltzmann factor, or we generally also call it as the partition function. Now partition function, here I would like to express, now according to Gibbs, so this partition function of canonical ensemble, according to Gibbs, the probability of finding this system in any one of its ith state at temperature T, where energy of that state is ER, so that is given as P of ER, that is directly proportional to exponential of minus B into ER. So the probability of finding this system in any one of its rth state at temperature T, where energy of that state is ER. So this is representing as PER, that is directly proportional to exponential of minus BER, where B, that is equal to 1 over KBT, where KB is our Boltzmann constant, and from this we can write it as the summation of PER, that is equal to C e raised to power minus BER, and taking the maximum probability, so PER, so that comes out to be summation of C e raised to power minus of PER, and this is equal to 1. So C value which we have find out, that is 1 over summation e raised to power minus B into ER, and this is generally known as the partition function, and we generally define this partition function as Z. So Z is summation of e raised to power minus B into ER. So this Z letter, that is the partition function, it stands for the German word Justendsumme. So this Justendsumme, so which means that the sum over states. So this partition function, it originated from this German word Justendsumme, so which is sum over state, and it is popularly known as the partition function. And this value of partition function, so it is different for canonical and grand canonical ensemble. So this partition function, it is this value, and this is for the classical system. Now in a system with quantum statistics, we can write this partition function. So in quantum statistics, so that is in terms of contribution from energy value, so that is equal to Z, which is summation of GR, so where R varies from 1 to n, exponential of minus B into ER. So this is for the quantum system when the energy value, so that is the degenerate energy value, so with the degeneracy, so that is equal to GR, so having different energy states. So in that case our probability relation, so it comes out to be GR e raised to power minus of BE R over summation of GR e raised to power minus BE over R, or we generally write it as GR e raised to power minus BER over Z. So that is our partition function. And in the classical statistics, where the energy it is having non-degenerate energy values, and the PER, so far classical system, so it comes out to be e raised to power minus BER over summation of e raised to power minus BER, which is equal to e raised to power minus BER over Z. So when it is having non-degenerate energy swing. So these are the relation between PR and ER. So now let us do a study, that is when we present a system in the canonical ensemble. Now let us consider this system as a member of canonical ensemble, so NVNT, in which the energy it is being shared by n identical system, so a ensemble which is having n identical systems, so they are contributing to this energy of the ensemble, and let an ensemble of this n identical system it is being labeled as from 1 to 3 up to n. So they are sharing a total energy of the ensemble, that is the total energy E. And let us suppose that the ER be the energy eigenvalues of this system, NR at a particular time t. So where R, that is from 0, 1, 2, 3, so and so, that is the state at how many systems they are having the same energy value at particular instant of time. So this we can write as the number of systems over energy. So N naught system they are having the E naught energy value at particular instant time. Similarly, when the time changes, so then N1 systems they are having energy value E1, N2 system they are having energy value E2, so and so. Similarly, N system they are having the energy value En. So we have a set of, so let us say we define it as up to a value of R. So we have a set of systems which is having different energy value at particular instant of time, and we generally represent it as NR, so which is known as the distribution set. Now this distribution set, it must satisfy this following condition, such as the total energy of all these systems at a particular instant of time, that is should be equal to the capital value of n, and it depend, suppose nr system, they are having a energy of er at rth state, so that is equal to n into u, where U is known as the average energy per system. So from this we can say U, that is equal to E over N. So that is equal to the average energy per system. Now any set nr of the numbers which satisfy this conditions 1, so let us say these are the two conditions, so which our canonical ensemble systems they must satisfy. So any distribution set nr of the numbers which satisfies these conditions 1 represents a possible mode of distributions of total energy E. Now, such a mode, it can be realized by number of ways. So, with how many number of ways these systems they are exchanging the energy within this ensemble, and that number of ways, that is generally represented as WR. So, which is equal to gamma function of n over n naught factorial, n1 factorial, and 2 factorial, so and so. So this we can write it as summation of system from 1 to r, which is equal to nr factorial. So here this omega is known as the number of ways for which ensemble can exist. So it means that ensemble can be in any one of these numbers, and for most probable mode of distribution, so that is the most probable mode of distribution. ਹੁਣ ਮੋਸਟ ਪ੍ਰੋਬੇਬਲ ਸਟੇਟ ਕਦੋਂ ਹੋਏਗੀ, ਜਿਸ ਪੁਆਇੰਟ ਦੇ ਉੱਤੇ ਜ਼ਿਆਦਾ ਸਿਸਟਮ ਜਿਹੜੇ ਆ they will attain the same energy. So most probable mode of distribution, so at that point of time we will maximize this number omega r, and sorry, so we will maximize this omega nr value, and the most probable mode of distribution, so at that point of time this number nr, that is represented with a term that is equal to nr star. So we denote this set as at a most probable mode, so this omega nr value, just a minute, so omega nr, so that is equal to n factorial over summation of r, which varies from 0 to infinity, into nr factorial. And since this n, that is the number of systems within the ensemble, they are very large, so taking log on this both sides, so this we can write it as log of omega nr, so that is equal to log of n gamma function minus log of summation of r varies from 0 to infinity into nr factorial. So using this Stirling's formula, so this becomes So log of n factorial, that is n log of n minus n minus this log of summation of nr factorial, that becomes summation comes outside, so that is nr log of nr minus nr. So this we can write it as n log of n minus n minus summation of this nr. This we can write it as nr log of nr minus, and minus this becomes plus, so summation of nr, so this summation of nr, that is equal to capital N. So this plus n and this minus n, they get cancelled out, and what we will left with is n log of n minus summation of nr log of nr, where r varies from 0 to infinity. So let us say this is our equation number A. Now at this point of time, if we shift from this set nr to a slightly different set, so if we shift slightly from a set nr to nr plus sigma of nr, where sigma of nr, that is a very less value as compared to nr. So then this above equation A, or this above expression, so we can change it slightly as this curly of log of omega, so that comes out to be equal to, so this is minus sign, so minus summation of r, which varies from 0 to infinity, curly of nr log of nr plus nr over nr curly into nr. So this equation becomes curly log of omega, that is equal to minus summation of r from 0 to infinity, curly of nr into log of nr plus curly of nr. So this we can write it as minus summation of curly nr log of nr plus 1. So this is our equation number B. So this we can rewrite as minus summation of r from 0 to infinity 1 plus log of nr into curly of nr. So let us say this is our equation B. Now this different state at that particular instant of time, so it must satisfy the conditions which we have written already. So this curly of nr distribution set, it must satisfy all these conditions, such as this summation of curly nr, so that should be equal to 0, and the summation of er of curly nr, so that should be equal to 0. So let us say this is equation number C and this is equation number D, and if we multiply this C with multiply this equation C by minus alpha, and equation 4 or equation D, you can say this is C and this is D, so by minus of beta, and when we add it, so what we get is minus of alpha summation of curly nr minus beta of summation er into curly nr, that is equal to 0. So let us say this is our equation number E. Now if this set, that is nr, it is having the maximum or the most probable value, so this most probable value, so at that point of time the curly log of omega, so this equation must vanish. So curly log of omega, that should be equal to 0 at the most probable state at maximized value. So when this equation vanish, so we can rewrite our equation, so that is B equation. So equation B becomes, that is minus of summation r from 0 to infinity. So at that point nr, that is equal to nr star, that is at the most probable state, curly of nr, that is equal to 0. So let us say this is our equation number F. So if we add this E and F, so adding E and F, so this equation becomes minus of alpha summation of curly nr minus of beta summation of er into curly nr minus of summation log of nr star plus 1 curly of nr, that is equal to 0. So this equation, that is equal to 0. So when I combine all those equations, so this becomes minus log of nr star plus 1, that is equal to minus of alpha plus beta into er, so that is equal to 0. So if I remove all those summation values, that is summation of curly nr, so that is common in each case. So if I remove all those values, so we get this equation. So from this I can rewrite as log of nr star plus 1, that is equal to minus alpha minus b into er. So log of nr star, that is equal to minus 1 minus alpha minus b into er. So this I can write it as minus alpha plus 1 minus b into er, that is equal to log of nr star. So this nr star, that is the number of distribution set at the most probable distribution which is having the maximum value. So at that particular, when the temperature between all the systems, so that is constant. So nr is equal to exponential of minus alpha plus 1 into exponential of minus beta into er. So let us say this is our equation G. Now this nr expression, I can write it as equal to C into exponential of minus b into er. So C is this exponential of minus alpha plus 1, that is a constant term and which is a indeterminate parameter. So this parameter we will talk more in detail in the grand canonical ensemble. So this is an indeterminate parameter and we generally consider it as a constant. And second, we know that the summation of nr star, so that is equal to capital N. So therefore this summation of nr star, we can write it as equal to summation of c e raised to power minus b into er, and from that we can find out the value of c. So that comes out to be n over summation of e raised to power minus b into er. And nr star, we can putting the value of c, so nr star over n, so that comes out to be exponential of minus ber over summation of exponential of minus of ber, and this denominator term, that is generally known as the partition function z. Now according to conditions. So what are the given conditions? So it is given that summation of NR into ER, that is equal to capital E. So putting the value of this NR star here at the maximized point, so NR star, so it comes out to be equal to N into exponential of minus BER over summation of e raised to power minus B into ER. So this NR over N, that is generally known as the probability PR. So that is the maximum probable state PR. So this PR, we can write it as NR star over capital N. So that we generally represented in terms of eigenvalue NR. So that is equal to exponential of minus BER over summation of e raised to power minus of BR. And from that we can find out the average energy per system, which is E over N. So this comes out to be summation of ER into exponential of minus BER over summation of e raised to power minus BER. So this we can write it as summation of ER, and this is equal to PR. So that is the probability. So this is the relation between ER and PR, and that is very important. So using this relation we will find out the connection between this statistics and thermodynamics, and this is all about for today's lecture. And in our next lecture we will drive out the various thermodynamic parameters, so which we can find out from these PR and ER values. So till then, goodbye, see you in the next lecture. So if you have any doubts, you can write your doubts, queries in the comment box, or you can ask me on WhatsApp. Okay students, goodbye.